I'm very delighted to be able to invite Dr. Bern Lin. In fact, it is a great honor that Dr. Bern Lin will be able to come to NTU and the Semiconductor is joining Colloquia to give this distinguished lecture. Before I hand over the microphone to Dr. Bern Lin, let me give you introduction on Dr. Lin. The list of his achievement. I have 2 pages of that. I think that you can see that he's a 中研院士, and also 2 years ago he received IEEE medal. Okay, and also that another one is the 2009 IEEE Plato Brunetti Award. Okay, another award. Okay, and that particular thing that the Brunetti Award, I think earlier 2 IC inventors also received this award. Is also the U.S. National Chemical Engineering members. Okay, it's a life member. So a lot of award, and then continue here that the Dr. Lin, in fact, obtained his bachelor degree from National Taiwan University in 1963, and then he went to Ohio State University to do his PhD, and then joined IBM. After IBM, I think he formed his own company called Innovation. Lean Innovation, just like the Lean Sanity. Okay, Lean Innovation. And in 2000, TSMC very fortunate to have him to come to work for TSMC. Very importantly, not only he has such a long list of very distinguished academic achievement, and so many awards. Also, very importantly, his innovation will contribute a lot to the technology. Okay, not just to TSMC, but also to the whole world. So, without too much introduction, let me please welcome Dr. Bern Lin.
Thank you very much. Well, I think the honor is mine to be able to come here for a lecture. I can see Alex there, even though you masked yourself. Okay? No? Okay. Well, let me tell you a little story about the Department of Physics in EE. When I was taking the exam for college entry exam, at that time, the physics department was very hot. The entry level was 430 points. and for EE, it was 424. Okay. So, well, at that time I was already a Christian, so I asked the Lord whether he wants me to come to university to study or went to a seminary, okay, and study. Yeah. So, so I followed both paths, but what in my entrance exam, when I put down my list, I only put down 13 wishes. Okay, usually people put more than 100, right? Because there were about 100 choices. So it's just a list by chance. And of course, people put medical school and then physics and so forth. But I have decided, because there was a EE student, who was 1 year earlier than I consulted him and he said, "Oh, you have to come to EE even though you love physics. Because, for physics, if you don't think you are a Nobel Prize material, you're going to suffer." Okay, so I said, all right, I'm not a Nobel Prize material, so I decided my first preference is EE. So I put down my first preference was EE, and the second was civil engineering, and physics was about the 5th or the 6th. That's a joke because medical school was the 13th of my list, and that was it, the end. Okay. Now, so I went to the exam and I got a score. Oh, the entrance was 423. I'm sorry, 423 was the entrance mark, and civil engineering was 425. Physics was 430. So when I got my score back, guess what I got? I got 424. It's precisely in the middle. If I got 425, civil engineering, 423, and 424 is electrical engineering. So I think my God put me in electrical engineering. All right. Okay. Let me go to.不是，我是另外还有一套书，这一套，这一套，这一套。Okay. All right. I'd like to talk about principles and applications of lithography, and we are pushing lithography to resolve 1/20th of the wavelength. Nobody thought of that, neither did I, about 1/20th of wavelength. So I'm going to tell you how we got there. First of all, how many generations are there? When I was in the field of lithography, we were dealing with 5-micron lines, which means 5-micron lines, 5,000 nanometers. Oh, I have one sorry. Okay. So let's define, this is one generation, 5 to 3,000 and so forth. 21 generations. This is already a product. This is going to be a product within a year. Okay, and then we are working on these. So, and we don't know where it's going to end, but at least there are 21 generations during my career when I first joined IBM in 1970. Okay? Okay, what does it mean? What does 1 nanometer mean? This beautiful lady's hair, you pick one piece and magnify it into this, that represents 80 microns. At the 28 nanometer technology, you can put so many SRAM cells on this cross section, on one piece of this. Okay, that many cells. Because this diameter is this, okay? And we look at at that time, in 1978, this was the size of a contact hole, okay? Several microns. 202, that was the size of an SRAM cell, and by 28 nanometer, this is the size of an SRAM cell. And this is the size of a virus, okay? So how many SRAM cells do we have? We have a lot within this and within this contact hole. That's what we are playing with. Okay, and this is the tool we use. The tool actually looks quite simple. You got an imaging lens that will reduce the pattern on the mask 4 times down. Well, here we have professors who work on microscopes. You actually reduce by 1,000 times or whatever, right? This is only a demagnification of 4. And you got a pretty complex illuminator there. I just draw it a very simplified way. And then it comes down and it exposes photoresist on the wafer. And that's basically our tool. Now, how real is this tool? Well, this is the actual tool. This is a lens, the imaging lens, and that is an illuminator here. And here is a stage where you put the wafer and so forth. This tool, an immersion tool, nowadays costs you $50 million. Okay. Now, if we are talking about EUV tool, it costs you $120 million and up. Okay. By the time we go to manufacturing, probably will be $150 million, about 3 times this tool. Okay. Now, I just highlight the lens for you to show that it's a huge lens. Well, I haven't put people in there, but when you look at, then you know the real size. This is the stage, okay? Now, the stage, this is stage. The stage is here, and that's how it moves. It's got scanned in high precision. And on the mask plane, you scan the mask at 4 times the speed as it down there. Here we're talking about scanning at 800 millimeter per second. Up there, 3200 millimeter per second. Very fast, very fast. And you have to keep everything precisely within nanometer. Okay, that's why it's so expensive. Okay, and now we have people. So you see how it compares with people. Okay, and people can even crawl down to examine. Here, these 2 guys, one of them is I. I was there. We were looking at the first immersion scanner that came to TSMC. And we're looking at the wafer stage, looking at the immersion hood there. Okay, let me get started with some fundamentals of image formation in air. Why in air? Because I'm going to talk about image formation in resist. It's completely new phenomenon when you go into the resist. So we separate it into 2 parts. Image formation in air. Again, this is a very simple plot. We just represent that huge lens. By the way, that lens costs you about $20 million. Okay. And it weighs several hundred kilograms, so that nobody can move it. They have to use a crank to move the lens. And yet, that lens cannot be dropped or impacted or whatever. Okay, they have accelerometers on the lens, so that when it's unpacked, you look at see whether there was acceleration history or there was some impact there. Okay, so anyway, this is a simple lens, and the purpose of this lens is very easy. There is a point here. You want to image a point back here perfectly. Okay. Now, anyone who knows about wave knows that you can never do that. Okay. When you have an excellent lens, perfect lens or whatever, because of the wavelength of your light, you get a pattern like this. It's a finite cross-section and so forth. Okay, and what is it? It's 1.22 lambda over NA. This is an arbitrary number. It depends on how you capture your image, but it's in the vicinity of 0.5 to 1.22, about that range. Okay, so you get a pattern like this. Now I'm going to explain to you what happened to cause this. Before we go to that, that is a real lens. The simple lens becomes like this. You have to put many pieces of glasses in there. When we go to so-called laser lithography, the bandwidth is very narrow. That's why you don't have other glasses to compensate. Okay, so you really have to design the lens very well. And well, anyway, this was a dry system. If you want to do an equivalent immersion system, it's like this, the same NA. But we're going 0.9, and the NA 1.32, then it's bigger. Even though the dry NA is similar, but then on the upstairs, here the sine theta is only 0.225, and here it's 0.33. Okay? And the reason this lens is expensive is that every piece of glass or of quartz has to be very homogeneous, and you have to make the surface configuration precise to 1/50th of a wavelength. Okay, you really have to make it very smooth and very precise, and then you have to position all this, centralize all this within a fraction of micrometer. Okay, so what do? You would assemble several groups first to the best of your knowledge. I mean, and then you test it and you see how much is off, and then you will try to compensate with when you add the other pieces in there, and you have to calculate in real time. You measure the result and you calculate and you find out how much shift, okay, you have to do the other ones. And finally it came back to that lens. So the assembly of that lens is also very, very tedious, very hard. All right, now let's go to wave. The lens is designed that when in all the optical paths through this lens, now I draw the wave, right? And you look at this, at the beginning was at the zero of the optical path, and then you got a wave going on, and here the wave stops at somewhere close to the end of the cycle. This is the same thing. It's the same number of waves that go through here and there, because it goes through a thicker part of the lens, so the optical distance is equal. So the design of a good lens is to make sure that from any direction, all the optical distances are equal. Then you form a perfect image. Okay? So based on that, if that's the case, you can represent the wavefront as a spherical surface. You have a perfect wave coming over and form an image here. Optical distance being equal from this point to that point. Okay. Now the problem comes is that what if you are not on axis? You are x off axis. Then you have a difference in these two paths already, right? If here is equal to each other, and obviously there will be a difference in the optical paths in these two. So what is it? We went through all the trigonometry and geometry, and we found that this distance, the difference in the optical distance, is x by sine theta. All right. So x by theta, if this d is equal to 0.5 lambda, then the two waves would compensate for each other. One is plus, the other is minus. It becomes 0. Okay. So we arbitrarily say, okay, that is my this is my criteria. I have to keep all the waves within 0.5 lambda. If that's the case, and then you'll find that x is equal to 0.5 lambda over sine theta. Okay, that means you cannot move this above this. When you are above that, you pass through 0, and it will be you will pass 0, and you will be in this region. All right. So in reality, is less than 0.5 lambda. That is the resolution criteria. Okay. Okay. So that's the case about resolution. If you move too far away, you lose resolution. And we also want to look at the case of depth of focus. What if I keep this the same, but I'm out of focus this way in Z? When that happens, you also have some geometry to solve, and then it becomes d equal to z sine squared theta. That difference is this. So you go down here, also assume d equal to 0.5 lambda. Then you have a lambda dependency as the same as x, but here you have the square theta, sine theta dependency in depth of focus. So what it means is that you are going to lose depth of focus faster than you lose resolution. Okay, so if you want to improve your resolution, you can reduce the lambda, but the effect is the same as in resolution or in depth of focus. You lose depth of focus and resolution in the same order. But then, if you try to improve the resolution by changing sine theta, then you have a convergence of depth of focus very quickly. So there comes these two equations. That's the equation for resolution. Lambda linear relationship to resolution, and lambda linear relationship, and there is sine theta and sine squared. This is theta over 2 instead of theta you just saw, because I'm using a non-paraxial scaling equations. The previous one was for paraxial. Okay, so that is two key equations that we use in lithography. One is resolution, the other is depth of focus. And how many handles do you have? I want to reduce it to 1/20th of a wavelength, right? That's one. Well, wavelength, well, we can change the wavelength for resolution. We can change the sine theta for resolution. This is how big your lens is. The wider the lens with the same focus, then you have a larger numerical aperture. And this sine theta becomes larger. And there's also this K1. If you have a way to manipulate this K1 and make it smaller, then you can improve your resolution. Okay. And so I'm going to show you several different ways to improve resolution. Okay, let's get some idea on what's going on. Here, when we are doing in TSMC, 250 nanometers with a quarter micron node, we use lambda equal to 248 nanometer, and we also use NA equal to 0.5. NA in this case is equal to sine theta. We use a sine theta equal to 0.25, and okay, I think I'm going to use the pointer. Okay, we use 248 nanometer wavelengths, and sine theta equal to 0.5, K1 equal to 0.63. That gives me a resolution of 250 nanometer. At this stage, I'm plotting the desired pattern. The target pattern is in red. And then these are contours. These are contours. I call it constant intensity contours, meaning that if I expose very hard, I get a line that's very wide. If I expose very light, I got a very small line, okay? And you can look at the line length. Now, the exposure that can give you the desired line width is this one, okay? Now, look, the line end is a little bit longer than the desired line length, okay? That is very unusual, because we're working at a relative K1 equal to 0.63. Later on, we're going to push K1 to much smaller, and then we're going to see how it became. Here, K1 is equal to 0.7. That's what we use for our 0.18 micron node. When we did that, look at this constant intensity line. That is my desired line width, and the line length is what? Very short, very short. And here is even shorter, K1 equal to 0.42 for the 0.13 micron node. Same wavelength, but we change the NA, increase the NA, okay? And then we lose the line end. And we, in addition to changing the NA, we also help with pushing the K1 down, all right? So what we lose is this line end, and we have to compensate for it, okay? Now, since that's the case, why don't I use this? This is so much more beautiful than this one. The reason is money. This is going to cost you more. If you go to K1 equal to high K1, you need very high NA. That means the lens is going to be much more expensive. If my competitor is using a lower NA lens, the cost is lower, all right? So I have to use, whoever is a better lithographer can take advantage of a lower K1 and make a good image of it. Okay, that's how you measure the competence of a lithographer. And you ask him, oh, what K1 you're using today? Oh, I use 0.5. All right. In the good old days in IBM, I went to the manufacturing guys. I said, you should use 0.65 K1. He said, no. We want 0.8 K1 because we're like this and we like the pointer to be square and all those good things. But it's a lot of money. It's a lot of money. You have to go to a much more expensive tool to get it. Okay? So the trend is that we have to push K1 to as small as possible. For immersion lithography, we're pushing K1 to less than 0.4. Actually, we have cases where we're pushing it close to 0.3. That's very scary. Look, this is 0.42. We already have pictures that look like this. Okay. Yeah. Okay. Then we look at depth of focus. We look at depth of focus. K1 equal to 163, 0.7, and look, in focus, D of focus equal to 0. In focus, of course, this is very nice. But when we go to this K1, this doesn't look as nice, right? Because if this is very dense, that means if you change the intensity, the line width doesn't change much. This is, but here, if you change the intensity slightly, you change the line width. Okay, so it's less sensitive. This is less sensitive to variation of light, and this is more sensitive. That is when you are in focus. When I'm out of focus, it's the same system. I lose depth of focus very quickly, and this one I still have some usable depth of focus. So the moral of the story is that you want to try to use K1 smaller, not only because of cost and also because of depth of focus. Okay. All right, let's talk about image formation in the resist. Now, what we'll just talk about is the so-called aerial image, the image in air or in vacuum. Now, we have to look at what happens in the photoresist. Now, I assume that I have such an image. That's called latent image. That is also my aerial image. My aerial image goes into the photoresist, and then it creates such an exposure. Okay, after you expose the resist, you have to develop it, right? Because the purpose of the resist here is that you want to have an opening so that you can etch this down, okay? The main purpose of all this lithography is that you have these openings at the right place you want. And then you open it up and etch it down. And here is a positive resist system. That means wherever you expose, it's going to be opened. You use the same aerial image and use a negative resist system, then you are retaining the place that was exposed. This is a negative resist system. All right. Now, did any of you notice that this shape is different from this shape? And this shape is different from this shape? That means your developed image is different from the aerial image. Here, I replicate this shape, and you can see that this is slightly larger on top, and this is slightly smaller on top. Okay. So what's happening? Well, actually, when I was teaching in Taiwan, that was one of the exercises I gave the students. I asked them to simulate the developed image, okay, and how, because when you develop, it's a gradual process. First, you open this up. Okay, and then this surface is now open under attack of the developer. It's the same as this one. Okay, now you have a new surface to be etched sideways. So now the top surface has more time under the developer than the bottom surface. Therefore, it got developed more and it goes out. Okay. Now when you turn it to a negative system, it's the other way around. The top has more time to be exposed and it got developed more. So it becomes a little bit straighter than the aerial image. Okay, that's the first thing that happened in the photoresist. Okay, now these are all the other things that happen to resist. So because of time, I'm not going to go through them, but I'm going to go through this one: multiple refractions. And there are three situations that they all are very important. So let's go through it. When your light goes into the photoresist, it goes to multiple refractions because now none of this surface is perfectly anti-reflection. So you have light reflected from this surface and you have light going in and reflected and induce multiple refraction. So what happened? Well, first of all, the effect of this is standing wave. Standing wave means you have a wave coming in and you have a wave that goes out. And the interference of this wave, the result is that you got a wave that is, I didn't plot the standing wave. The standing wave it will not be propagating anymore. It will be peaks and valley, stationary. That's why it's called standing wave. And it's most prominent when you have an aluminum substrate because aluminum is highly refractive. So your reflected wave is almost like 95% or higher than the incoming wave. So they form very strong interference between them. So what happened? Well, so when you have a very good refraction, this will be, you got to know, no exposure. No matter how hard you increase your intensity, that is the point where there's no exposure, okay? And that was, when the good old days, people were trying to use negative resist. And now they are standing waves. And on the surface, if you're using an aluminum surface, there's no exposure at the bottom. No matter how much you increase your illumination, there's no exposure there. So people lose the photoresist. There's no exposure. You lose it. And they blame it on adhesion. Oh, you got a lousy chemistry. You got a lousy adhesion promoter. And no, because of standing wave, okay, you lose that adhesion. Okay. Okay, this is some experimental proof. Here is a standing wave here. Unfortunately, the picture was not taken by me. So okay.